In this section we look at the next two polyhedrons, pyramids and cones. We will start off with pyramids. A pyramid is a polyhedron in which one face can be any polygon, and the other faces are triangles that meet at a single common point. That's the official definition, but you probably already know what they look like. You have undoubtedly seen many pyramids before. Here are the famous ones in Giza. This is the famous Luxor Hotel in Las Vegas. This is the Pyramid Arena in Memphis. And this is the Walter Arena on the campus of Long Beach State. Plus there are so many more examples. You have probably seen a lot of pyramids. But all those pyramids I have just shown you, and by far the most common pyramid out there in the world today, are all square pyramids. The bottom of all of those pyramids is a square. However, the definition of a pyramid clearly says that it can be any polygon, so it doesn't have to be a square. You certainly could have a triangular pyramid where the bottom is a triangle. This is most commonly seen in a four-sided die, for those of you who have actually seen a four-sided die before. That same triangular pyramid on the left can be seen in this die here. Pentagon on the bottom, then it's a pentagonal pyramid. Hexagon on the bottom, then it's a hexagonal pyramid. You probably get the idea. Just like prisms, pyramids are made up of faces. Every side of a pyramid is a face. And also just like prisms, the faces are split into two groups. The polygon on the bottom that we've been talking so much about is called the base. Obviously, a pyramid only has one base, where a prism has two. The other faces other than the base, which will always be triangles, are the lateral faces. Again, just like prisms, pyramids have edges. All of the black line segments are edges of this pyramid. The edges of the base are the base edges. Where do they get these names? I have highlighted the base edges in red here. The other edges are the lateral edges. They are red now. You could have probably guessed, but the vertex of a pyramid is the point at the top. Another one that we have done so many times now you probably could have guessed, but the altitude is the perpendicular segment from the vertex to the base. The height is the length of the altitude. Another vocab word we have done many times now. Considering what a right prism is, you might have been able to guess that a right pyramid are the ones that are straight up and down. The altitude will touch the center of the base in a right pyramid. Oblique pyramids are incredibly rare, but would look something like this. This is another instance where you can assume a pyramid is a right pyramid unless you are told otherwise. A regular pyramid is a right pyramid with a regular polygon as a base. Almost all the time we will be dealing with regular pyramids. Non-regular pyramids are not common at all. Everything is symmetric in a regular pyramid. All of the lateral faces are congruent isosceles triangles. Slant height is the last vocab term for pyramids. A slant height only exists for regular pyramids. A slant height needs all of the faces to be congruent so that there is only one possible length. A slant height is the length of the altitude of one of the lateral faces of a regular pyramid. So it is not the height of the pyramid, but a height of one of the lateral faces. You need to keep those straight. Imagine you are standing at the top of the Luxor in Las Vegas. From the vertex you decide to slide down the side of one of the lateral faces just because you are crazy like that. You would have traveled down the slant height of the pyramid. I chose this as an example because they actually did that one time on Fear Factor. They slid down the side of the Luxor. For whatever strange reason, the slant height is abbreviated with a lowercase l. Here I have a slant height in red for both of these pyramids here. Now we get to cones. A cone acts extraordinarily like a pyramid, just with a circle for a base. I'm going to go through the vocabulary for a cone pretty quickly since it should be somewhat familiar by now. A cone has a base. Just like a pyramid, there is only one base, not two. A cone has a vertex. A cone has an altitude. The length of the altitude is its height. A cone has a radius. Just like a cylinder, a cone's radius is defined to be the radius of its base. Right cones stand straight up. In a right cone, the altitude will hit the center of the circle. Only in right cones do we say that there is a slant height. Just like a pyramid, it would be like you decided to sled your way down the side of it. Oblique cones are about as useless as the other oblique shapes, but this slanted thing that looks like a spotlight on a stage or a dunce cap is an oblique cone. We won't be dealing with these, so you can assume something is a right cone unless you are told otherwise. Now it's formula time. This is the formula for the lateral area of a pyramid. The P stands for the perimeter of the base, just like the P in the prism formula. I told you earlier that for some strange reason the slant height is abbreviated with a lowercase l, so that's what this L is. The formula is 1/2 times the perimeter of the base times the slant height. In the last section, cylinders were so similar to prisms that you could use the same formula. The same is true here. Cones are so similar to pyramids that you can use the same formula if you like. However, just like last time, you can also memorize a cone-specific formula if you like. We know that the perimeter of a circle is 2 pi r, so we can substitute that in for p. We aren't done though. The 1/2 and the 2 cancel each other out, so the cone-specific formula is simply pi rl. Like the last section, you have a choice to make. You can decide to just use 1/2 PL for both pyramids and cones. You will have an extra step as you substitute in for P every time, but it is doable. Or you can memorize a new formula, the pi RL, and it will save you a step whenever you are solving for the lateral area of a cone. The choice is yours. For the surface area formulas, let's revisit prisms quickly. A prism has two bases, so when we did the surface area for a prism, we took the calculation for LA and then added in the area of two bases in order to get our surface area. We simply added in the two pieces we were missing. We are going to use the same kind of logic for a pyramid. However, for a pyramid, we only have one base, not two. So when we want to calculate the surface area for a pyramid, we only need to add in the area of a single base. That's why this is the formula. Cones also only have one base, and cones work so similarly to pyramids that we can still use the same formula if we like. That formula will absolutely work. You can probably guess where this is going, but for a cone, we know what the base is. It's a circle. So we know that the area of that base will be pi r squared. Substituting that in, and we get that the surface area will be lateral area plus pi r squared. You once again get to choose whether you want to memorize a new formula to save yourself a step or not.